Welcome everyone to geometry. We want to take a look today at non-Euclidean geometries. And this is going to be a pretty informal introduction to them, really not a very in-depth discussion at all. So a little bit of fun stuff, so a little bit different presentation for the first part, and then for spherical geometry. But anyway, let's take a look at this stuff. So first, really briefly, let's look at our notes. And there's a bit of an introduction here that I would encourage you guys to read through, especially for this first bit, to try and take a look at that and go ahead and do those things that it asks to. And then we're going to fill in this blank here shortly. And then what we're going to do is we're going to look at a model for our geometry. So, all right. So spherical geometry, also called elliptic geometry, is probably it's actually a little bit more well known than you realize, because it's actually the geometry of our Earth, right? Of Earth, our planet. So we want to consider that to be a great example for us, right, or a model. So we have to understand a few things, what exactly is going on, and some of the language that they use here is actually really quite appropriate, but leads into some other courses as well. So let's go ahead and leave this for a moment, and we're going to just consider the model and then come back and fill in this blank, and then come in and take a look at our a few different things here. All right. So okay, so let's stop the share first. All right, so for a spherical geometry, we could consider a sphere. So here I have one of these great, fantastic kickballs that I'm sure you all have great memories of. And we want to consider this our surface. This is our plane. Our plane is not flat. Our plane is a sphere, right? A plane is simply the collection of all points in the geometry. So for this geometry, the plane is a sphere. And then we want to decide, okay, what is a line? What is a point? What is a circle? This sort of a thing. So on a sphere, the easiest way to think about a line is actually to think of it kind of like the shortest distance. So when we think of 2 points on a flat plane, we just say the line is the straight line between them, and right, that's what gives the distance between them. And so we can, when we think of a sphere, what does the shortest line look like? So if I were to consider, well, here's a great example. If I were to consider the two sides here, would it be shorter for me to go straight across to get from one side of playground to the other, or would it be shorter for me to go up and over? Right? If you think about it, well, this looks like an arc, and to your perspective, if I can get this right here, right, this kind of looks like a straight line. But in reality, right, I'm still doing this motion here. So in a three-dimensional space, I'm still traveling on a circle. But that circle that I'm traveling on is a circle whose center is the center of the sphere. So when we talk about traveling on a line on a sphere, you're going to put a rubber band around the sphere. If you put it too far one way, it's just going to slide off, right? So they have to be cutting the sphere in half, essentially, or very close to it. So if we think of the rubber band as cutting it in half, that way it stays on. This is a line on a sphere. So a line connects back to itself because it's essentially the largest circle you can draw on a sphere. And when it hits that point, it's actually called a line. So this is a line. And points on this line, right? This line represents the shortest path between any 2 points on it. If I were to pick out 2 other points, then let's see here. Well, if I were to pick out 2 other points, then the line that connects them would also be the same sort of line. And in general, in a very generic geometry term, it's called a geodesic. A geodesic is a line of shortest, or a path of shortest distance. So that's interesting information for you. That's what we'll fill in on the notes. But so we get this line, and there are some interesting things to notice about it. Well, maybe not about this line itself, but if I were to say, all right, let's consider 2 lines. Okay. I got a second line on there. Is there any way that I can put that second line on there so it doesn't cross the first one? What if I move it this way a little bit? That didn't work. Let's see. Oh, no, no matter however I move this thing to, it's overlapping, or they're falling off, right? So here's my line. Any other line that I put on is going to cross the first one that I put on. And with that, if we consider Euclid's 5th postulate, the one about parallel lines, right? There are no parallel lines on the sphere. So in spherical geometry, there are no parallel lines. All right. And then let's consider something else. Let's consider a triangle. So let's pretend that, get this, we have the equator, and then we have a line of longitude. So they meet at a 90-degree angle. If I were to add another line of longitude, oh man. We're getting there. All right, I don't remember which is which now. But if this is our, if this is the equator, and these are 2 lines of longitude, then we have that these meet at a 90-degree angle and these meet at a 90-degree angle, which means that the triangle we have created with our 3 sides has an angle measure of 90 degrees, 90 degrees, and something else that's still larger than 90 degrees. So we have that the sum of the angles, the sum of the interior angles, is actually greater than 180 degrees in spherical geometry. The other thing we have is that if we were to consider one of the exterior angles, okay, this exterior angle is 90 degrees. Okay, it's not perfect. I could move that around, make it look a little bit better anyway. But the point is we have this one is 90 degrees. This is also 90 degrees, which means that when we consider the opposite, right, when we look at the triangle, the non-adjacent interior angles are not necessarily smaller as well, right? So these are some of the theorems that we've talked about in geometry so far for Euclidean geometry, and they seem to be failing here. Now, what's kind of interesting, it's a little difficult to get these to move around without having them fall off, but if I move this a little bit, or just take it off and put it on in a slightly different spot, you'll notice that this triangle that I've created, these 2 measures are still really close to 90, but this one is much smaller. So as we create smaller triangles, we actually end up with angles that are angle sums that are closer to the Euclidean 180 degrees. So smaller triangles will have or approach a sum of 180, but that sum is not fixed either. Okay, so it can change. The interior sum changes depending on the size of the triangle. And that gives some really interesting results as well. So this is our model of spherical geometry. All right, let's go ahead and pause this video for now, or end this video for now, and we'll come back and take a look at that model in our notes in just a moment. I hope you guys are having a great day. I'll see you again soon.